All right, let's get started. Quick announcement. The engineering open house is tomorrow. So the regular rooms for the discussion sections are not going to work because they're going to be occupied by the engineering open house activities. We posted, I think 2 weeks ago by mistake too early, the places where you need to go for the discussion section. So I'll ask the TAs to post it again, but to watch out for that post and go to the right place. Okay, the labs are not cancelled, but they're not going to be in the usual locations. Yeah. Okay, and I think many of you did well in the midterm. I think it was I guess problem 7 was a bit hard, but otherwise it seemed like okay. Yeah. So follow the course policies for regrade requests. Look at it carefully. Write down what you think is incorrect and give it to a TA. Okay, in the office hours or something. And if they have difficulty, they'll talk to me. All right, let's wrap up dynamic programming today, and if time permits, we'll start some basics of graphs. So we started this last lecture that the easy examples of dynamic programming are mainly on sequences, right? We saw a lot of sequence problems. Why is that the case? Because they are simpler structures, naturally they admit some easy recursive definitions, and it's easy to see the basic ideas in a simpler setting, right? But DP is a powerful technique, and it can be used, for many problems. And one other large class of problems that one can attack with DP is this tree-like, or in more generally decomposable structures. So what does it mean to be decomposable is a little bit technical. Even in graphs, you can define that in a formal sense. It's a little trickier. But let's just do a simple case like a tree, right? And so we want to solve the maximum weight independent set problem in a tree. What is that? I give you a tree, and every vertex of the tree has some weight, right? And some number, non-negative number. And we want to find a subset of the vertices that are independent. What does it mean? That they don't have any edges in common, right? Vertices such that they have maximum possible weight. Even on a tree, it is not obvious how to solve this problem, in the sense that nothing simple and greedy will work, because the weights are, even if weights are unit, it's not easy to solve this problem on a tree, okay? So we could apply dynamic programming, and we sort of saw that it is hard to apply dynamic programming on a graph, or at least not something that leads to a polynomial time algorithm. You can obviously solve it using recursion. So on the tree though, it sort of works in a nice way because it's decomposable, right? And what is a natural recursive idea? You say, like we did with the independent set, in a graph, you pick, the natural vertex to start trying to do recursion is the root of the tree. You could root the tree anyway, right? It doesn't matter really, because if you take an undirected graph, you are on a tree, you can root it anywhere you want, right? But once you root it, it has some nice structure. So you do the obvious recursion on, or not the obvious one, but the simple one, that I try to figure out whether the root should be in my independent set or not, right? And if you don't want it, then the problem nicely breaks up, because you say you throw out the root, then you get these two trees that you recurse on, because they're completely independent, right? Separate. So either you decide to include the root. If you don't want to include the root, then it decomposes nicely, and you recurse on two simpler problems, right? Or you decide to include the root, in which case you say, I want to include the root, which means I cannot include my children. Yeah. So you put the root aside, I have 10 weight already. I throw out A and B, because I can't include them anymore once I include the root, in which case if I remove root A and B, I get a whole bunch of subtrees, right? And I recurse on all of them and find the optimum solution, right? So that's the obvious recursion. If I keep doing that, you may wonder, what kind of problems will I generate? As I get, more and more trees will be generated, right? The only thing we need to think about is, will this recursion, as you go down, generate a lot of problems, or will it generate a small number of problems, right? And the observation is that at any point in this recursion, the only sub-problems that this recursion generates look as follows. that I give you a subtree rooted at one of the nodes, and you have to find the optimal solution in that, right? So we realize that there are only n sub-problems which will be generated in this recursion. So okay, if you memorize it, then we'll get an efficient algorithm, right? Okay, that's the simple observation. Yeah. So that's a nice thing about trees because they decompose nicely. So once you get that, you can write the recursion or something, but I'm going to go directly to the remember we give a name to it, right? We realize that the problem that sub-problems we generate are of the form solve the problem on a subtree rooted at a particular node u. So we'll define opt of u is the maximum weight independent set value in T of u, which is the subtree rooted at u, right? So what is opt of u? Well, there's two cases, right? Either we do not include u itself, in which case what do? We look at the children of u, right? And add up all their optimum values, yeah? Right? This is one case, right? We don't want to include u, in which case we look at the children of u and sum up all their optimum values, yeah? If you want to include u, we get the weight of u, right? But then we can't include the children, we have to throw out the children. What does that mean? That we recurse on what? The grandchildren of u, right? So we sum over the grandchildren of u, opt of u, okay? So what's the base case? The base case is what? What's the base case? When do we stop the recursion? Yeah, right? We stop the recursion when the u is a leaf, right? Yeah? What is the value for a leaf? What is the opt of a leaf? The weight of the node itself, right? Yeah? Because there's nothing to do, right? There's a single node. Clearly the optimal solution for a single node is its weight, right? You should just take it, yeah? Okay, that's the base case. Okay, and the natural question is, how do we evaluate these problems, right? You should do bottom up, right? If you want to make it iterative, that means you first evaluate the leaves and then you evaluate their parents and keep going on, right? So what does it correspond to in a tree to do that ordering? That you want to do the leaves first and only then their parents and then their parents and so on. What ordering of a tree gives you that? That you want to evaluate a node only when all its children are evaluated, all its descendants are evaluated. Yeah? Post-order traversal, right? So if you have a post-order traversal, then you can evaluate in that order, right? Yeah? Okay? So that's a simple code, but let me just run it on an example and then it's much more easy to understand what we're doing. So on this tree, what is the recursion really doing, right? So what is the optimum value at this leaf h? The optimum value is 2, right? For all the leaves, we can easily compute the optimum value, right? Okay. What about at D? What is the optimum? Well, here too it is 4, 9, these are easy. What about D? What is the optimum value at D? That means we are looking for the optimum weight independent set in the tree rooted at D, right? We just follow the recursion blindly, we don't think. Once we figure out the recursion, we just follow it, right? Right? It is a max of 2 quantities, right? Right? What is it? I don't include myself, in which case I have to sum the values at my children, right? Because I already know those values. So that is a max of 2 plus 7, which is 9, and or include myself, which is 4, and I recurse on my grandchildren. I add up the values of grandchildren, but I don't have grandchildren in this case, so that's 0. So it is a max of 4 and 9, right? Okay? So the value here is what? 9, right? What about at A? Now that I have all my children and all my descendants evaluated, what is the value at A? Again, I just apply blindly the recursion. I don't think, right? Once we figure it out, we don't rethink. We just apply the formula, right? Okay, but it's good to think. It's either the sum of the values at my children. What is that? 22, right? 4 plus 9 plus 9, right? Or I include myself, which is 5 plus the values at my grandchildren, right? 5 plus 2 plus 7, right? Which is better? 22, right? Yeah? So, okay, I put 22 there. What about B? Again, the same thing. It's either 3 plus 11 or 8 plus 8, right? Okay, so that is 16. What about at R? It's either 22 plus 16. What is 22 plus 16? 38. And or 10 plus, okay, we would add all this up, the grandchildren, right? What is that? Sum. The fast calculators around. Sorry? 53, that includes 10. Yeah? Okay, what is this? 18, 22, 33, 34 plus 10, right? 44, right? It is 44 versus 38. Yeah? Okay, what am I doing? I'm just following the formula, right? I'm not being any clever. I'm just adding up all the grandchildren's values. No, not the red ones, the blue ones, right? Okay, you're not adding the red values, right? Blue values. Okay? What is the sum of the blue values? 4 plus 9 plus 9, that is 22, plus 25 plus 11, that is 36, plus 10, right? That's 46. Sorry? Oh, yeah, why would we do that? We wouldn't do that, right? Because the formula is a formula, right? Okay, so it's 46 plus 10, 56 versus 22 plus 16, right? So we just do 56, right? So that's the value, okay? Okay, once you figure out the recursion, we don't think, we just implement the recursion. Yeah? Is it clear? No? Yes? Confusing? It's confusing only if you start looking again like, what am I doing, right? You know, but once we found the recursion, we just do the blind thing, okay? The recursion is the easy part, no? The correctness is easy. Once you think of recursively, its correctness is easy. Then the implementation, you shouldn't look again. Should I look at my grandchildren? No, we already figured it out. Yeah? Oh, it's only 46? Oh, okay. Okay, then that's fine, right? Oh, this is only 36 and 10. Okay, fine. Okay, still, yeah. Okay, good. Okay, any questions? Yeah? Okay, in terms of the code, just to be clear, you know, it's a very simple code because if you do the ordering of the vertices in post-order traversal, it's a single array and you can just do the same. How long does, this is an important technical point, how long do you think this algorithm will take to run? Okay, what's the running time of this algorithm? Okay, if you want to do it blindly, naively, okay, how many problems are we evaluating? So, right, this is a simple code, right, for I equal to 1 to n. What is the value of m of vi? It is the max of these two quantities, right? Okay. So, how long does this calculation take? Well, I have to sum up the values at my children, right? Then I have to sum up the values at my grandchildren, and then take the better of the two, right? And plus my value in one case. How long does it take? It depends on how many children and grandchildren I have, right? Yeah? Okay, if it is a binary tree, that's not very big, but it could be, tree could be big, no? So in the worst case, how long can I, what is the maximum time I'll spend on evaluating one guy? Sorry? N time, right? I can't have more than n time. So, right, a trivial upper bound is n square, right? Because if I spend n time at each guy and I'm doing n calculations, such calculations, the total running time is no more than n square. Is that okay? Yeah? Okay. But is it right? So what does it mean? Clearly it's upper bounded by n square, but is it a good estimate? Yes, when you have an upper bound, we also have to think, are we going to achieve this, or are we overcounting, or are we undercounting? I mean, we're not undercounting, right, because an upper bound, I proved it, right, but are we overcounting a lot? Okay. I claim actually the running, I'm not changing the algorithm, I'm just doing the same thing, I'm not optimizing it, but still I claim that the total running time of this algorithm is only O of n. Why is that? No, not because I saved the grandchildren. This is the one which is saving it, right? It is saving it and doing it. This is the iterative algorithm, saves and does it, right? But I'm just saying that it still takes only, the algorithm we ran, which is just the saving algorithm, I claim takes only linear time, not n square time. No, I'm not optimizing at all. You see, I'm just doing the naive thing I did, right? I still claim it takes only n time. No, it's not that. Okay, yeah. No, it's not because you care about the root. I'm saying, I'm doing the calculation. I'm not optimizing it. I'm just saying that, yeah, that the runtime is only O of n. Yeah. Exactly. Okay. So the claim is, instead of counting it naively as saying, each step of the evaluation takes n time in the worst case, let me count the total work in a slightly different way. Okay. How am I going to count? Like I said, look at a particular node. When do I access that value's node? When do I touch that value? I'll touch that value when I actually evaluate its value, right? I put that value in that array. But when does anybody need that value again? Who needs that value? Only its parent and its grandparent, right? Nobody else needs that value, right? So each node, each value is touched only 3 times. Okay? Right? Is that clear? So if you count it that way, then the total work is only 3 times n, right? Okay. So what is happening is that when I evaluate this guy root, I have to add a lot of numbers, no? Okay? True. So one step can take n time, but most of the steps are only taking even less than 1. I mean, how long does it take to evaluate a leaf? Only 1 unit of time, right? So this is called amortized analysis. What does amortization mean? Just averaging, right? So what this is saying is that, sometimes you can count differently so that you get a tighter estimate than just doing the naive counting. Okay? So that's useful. Yeah. So I'm not changing algorithm, not optimizing anything, nothing. Just telling you that, if you count a little differently, you will get a better right answer rather than a very crude overestimate. See, n square versus n is a big change, no? Because you said to evaluate one value here takes n time in the worst case. Because see, look, to evaluate r, I had to add a lot of numbers, no? I may. Yeah, I basically said that to evaluate one guy, I don't know the runtime exactly. In fact, I do know it is a sum of number of children plus number of grandchildren, right? So the simple observation is that, for any tree, if I look at each node and sum up the number of children plus grandchildren, it is only 3 times n and not n square. Okay. No, if you do a post-order traversal, why would you this is a very clean algorithm. See, V1, V2, Vn is a post-order traversal of the nodes of tree. You first computed in linear time, and then you're blind. I equal to 1 to n. It's a loop. You're not doing anything at all, right? It is just a simple loop. Once you have the post-order traversal, it automatically guarantees that you have all the right values pre-computed. Okay? All right. Any other questions? Yeah, it's an important point to understand this amortized analysis. If you do more advanced things, it's good to know that. Okay. So I want to do one more non-trivial example of tree-based dynamic programming. This is mainly for telling you a thing that you will see again in 421. But you see that the dynamic programming is a very powerful and important technique for programming languages, right? So this is called the CYK algorithm. I'll be sketchy a little bit, mainly to save time and also because it's the details are messy, but not once you get the idea, it's not particularly insightful after that. This is called the CYK algorithm. It's very famous, and it's sitting inside all your compilers, right? So what is the context for this, right? So we saw regular languages and context-free languages, right? We saw that regular languages are very simple in some ways, right? Why are they simple? They are not very expressive, right? For example, we couldn't even do 0 to the n, 1 to the n as a regular language, which means in particular that if you wanted to have a well-balanced parenthesis, which is very important in very simple calculations or expressions, it is not a regular language, right? So we went to context-free languages because they are a richer class of languages. Okay? So if you take your programming language, C, Python, whatever you are using, right? they are all essentially context-free languages, okay? Some variations of context-free languages. Okay, so what does it mean that there are context-free languages, and why do we use them? First, when you design a language like C or whatever you want, a programming language, you want it to be rich enough to express things that you want to express, right? That things like, I want to express arithmetic expressions, subroutines, recursion, things like that. You want the language to be able to support expressive ability, right? But then, once you make the language expressive, then you're stuck with the following problem, right? The parsing problem. What is the parsing problem? I give you the program and say, is it a valid program, right? You better have an efficient algorithm for it, right? If you can't compile your program, then the whole point of expressivity is useless, right? Okay? So when you design a language, as opposed to you're given some language, you're designing it yourself. So you have these twin goals of designing a expressive enough language so that you can do what you want, while you also have the goal of making the parsing easy for you. It can't be like very inefficient, okay? So that is the issue that when you design a PL programming language you face. So for example, this is I already put it up a while ago. This is sort of like the small piece of the C language specification as a context-free language. Okay, it's huge, right? It's very long and stuff. So that's what your compiler is doing, right? Your compiler is, when you write C or whatever, it takes your program and checks whether it is a valid program by going through the grammar specification of C, and checks whether in fact your program is a valid C program. Okay, so somebody has written down this CFG for you somewhere. It's very long. So what is the algorithmic problem that your compiler is doing, right? The first thing that your parser has to do is to take your program and check, is it a valid C program, right? So it gives you all these errors, right, if it doesn't compile, right? That's how it figures out. Okay, so more generally, what is the problem that we would like to solve? It is the following. I give you a context-free grammar, and I give you a string W, and I want to know, does W belong to this language generated by this grammar? Is the problem clear? Yeah? Is the algorithmic problem clear? I give you a grammar and a long string. For example, what is the grammar for your programming language? It's somebody has written that big grammar, right? Specific grammar for C. That's a context-free grammar. And then your C program comes along, and then the compiler has to check, is this a valid string generated by that grammar, right? Is that clear? Okay. So how do we do it, right? So here is an example, right? Okay. So first, we're going to make a simplifying assumptions because that helps us design the algorithm cleanly. I'll assume that the context-free grammar is in what's called Chomsky normal form. I didn't discuss it too much, but here is what is the Chomsky normal form. Every rule has only of the following form, right? A goes to BC, where B and C are non-terminals, or A goes to one letter A. Some alphabet letter A. Okay, that's the only productions allowed. It's simplifying assumption, right? To make it a little easier for parsing. Okay, so grammar is cut to be in Chomsky normal form if the rules are very simple like this, and every context-free grammar can be converted into something like this efficiently, and it makes it life easy. Okay, so here is a grammar, right? So everybody remembers grammars again a little bit. I know it's been a while, but grammar looks like this, no? S goes to epsilon A B X B, Y goes to A B X B, X goes to A Y, A goes to 0. So this is in Chomsky normal form because every rule is of the form non-terminal goes to two non-terminals, or non-terminal goes to one terminal. That's it. Yeah. So now I ask, is this in the language? Is this in the language? I can ask all these questions, right? So your algorithm should, given a long string, check whether it is in this language or not. Yeah. Yeah. Okay, how do we do it? We are in DP land, so when is a string in the language? What is the definition of string being in the language of a grammar? What is the meaning? When I say some string is in the language, what does it even mean? In a context-free grammar, right? So that the string should be derivable from S, right? If S derives that string, then it is in the language, right? Or equivalently, it is a parse tree for that string, right? that S derives two things, and then at the end we get the string we want. Yeah. So now we are talking about the inverse problem, right? Given a string, I want to know, is there a parse tree for that string according to this grammar, or is there no such thing, right? Yeah, that's hard, right? Because oh, maybe there are an exponential number of parse trees. I can't try all of them, right? Yeah. Okay, but then let's think a little bit more recursively, right? When does S derive a string W? What does it mean to derive a string W? S derives. How does the first step of the derivation look like? Because it's a context Chomsky normal form, you have to use some rule, right? S goes to what? Some A, B, I don't know which rule to use. And then what should happen? A should derive some string U, B should derive some string V, and U and V should give W, right? Okay, is that okay? So recursively, what we want to say is that, what is the definition of S deriving W? S derives W if, suppose the length of W is 1, then S must derive that letter, right? Yeah, I'm making some simplifying assumptions, right? So S goes to W must be a rule in the language. Okay, if the length of the string is 1, we are happy, right? Yeah, that's the easy case. What if the length of the string is long? Then S will derive that string if and only if there is a rule of the form S goes to AB, yeah? And then A derives U and V, B derives V such that W is concatenation of U and V. Is it okay? Yeah? Okay. Sounds good? Okay. Now this gives a recursive program, right? You'd say, S, you look at this, if the length of the string is 1, you check if any rule, there is a rule which says S goes to that letter, right? Okay. Otherwise, what do? For every rule S goes to AB in the rules, okay, and every split of W into UV, okay, check if A derives U, B derives V, and then W is UV, right? Okay, that's recursion because why? Because the length of U and V are less than the length of W, right? We have made the string smaller, right? That's why it's recursion, right? Is it okay? Okay, this looks like a humongous recursion, right? For every rule, every split, you try all possibilities, right? Okay, but at least we have a recursive program, right? Okay, yeah? Okay, now we have to ask the obvious question. What happens if we memorize it? Okay, are we generating a huge number of problems, or really are we generating a small number of problems again and again? So what do you think? Okay. Okay, so what does the recursion do? It starts with S, right, and says, okay, if W is the length of W is 1, we are happy, right? It's easy case. Yeah. Otherwise, it says for every rule S goes to AB in the grammar, and for every split of W into U and V, check if A derives U, B derives V. Okay? And then if it is, then we are happy, we say yes. If there is no such thing, we say no. Yeah? Okay? So, okay, but then as soon as we do that, what is the recursive problem going to try to do? The recursive problem has to solve A derives U, right? Where the length of U is one, at least one less than length of W. Okay, but how do we know whether A derives U or not? Again, recursion, right? To check whether A derives U, you have to check. Okay, if the length of U is 1, I'm happy, right? Because we have to check if A derives one step, there is A goes to that letter is there, right? Otherwise, A derives U if what? There is a split of U into two strings, right? And a rule A goes to BC such that B derives one part and C derives the other part. Yeah? Is it okay? Again, I'm doing the right? Yeah? Okay. Now I get this humongous recursion, right? But what does the structure of each of those sub-problems look like? What am I generating? Not as a tree. I may generate the same thing again and again, no? I may generate A derives U many times, right? But I want to know what are all the parameters that I'm floating around here, right? So one thing is, clearly, we need to know for every non-terminal, we need to know whether it is deriving some string, right? But I want you to focus on what, if the original string is W, what type of strings am I getting as I go along, right? So I start with W, right? And then I split it into two strings, right? Arbitrarily. I have to try all possible splits into U and V. But then what happens to those strings, again, when I do the recursion later? They split into two strings, right? Okay? So at any step, what does one of those strings look like when comparing with the original string? It's a substring, right? Okay? Is it okay? So any string I generate in this decomposition is a substring of the original string. Yeah? It can't be a subsequence, right? Okay? So what I'm saying is, if I start with W1, W2, Wn, my recursion will split it into two pieces, right? Arbitrarily, right? But once I get this piece, I'll split it further into some way and I get one more piece like this, right? So, but what is this piece? This piece is actually some substring of the original string, right? Okay. So how many sub-problems am I generating? The number of substrings, okay? And what is the other parameter? Which non-terminal should derive that substring? Okay? So the only sub-problems I get are one non-terminal, one substring, right? But there are polynomial number of them. Why? Because the number of substrings of a string of length n is what? Only n squared, right? As we saw in the palindromes. And how many non-terminals are there? That's the size of the grammar, right? The grammar has 10 symbols, then the size of the grammar should be part of the input, right? So the number of sub-problems we generate is r times n square, where r is the number of non-terminals and n is the size of the string. Okay? So if you memorize it, you will get a polynomial time algorithm. That's it. There is no magic to this. Okay? Okay, the only thing is, we go back to the recursive definition of what does it mean for S to generate a string in the grammar. And we did the obvious thing. We didn't do anything clever, right? We tried all possible ways of splitting that string, all possible rules, and we just did the obvious thing. But the only thing we observed is that the structure of the subproblems is simple, right? That we only want to know whether a non-terminal generates a substring. So you can, I'm not doing the recursive code. We just have these subproblems. The subproblems are of the following form: a non-terminal, an index I and an index j, where I is less than j, which means that derive aij means 1 if non-terminal A derives the substrings wi to wj. Okay? So these are the only problems I am interested in. Okay? And the base case is when the length of the string is 1, which means j minus I is 0, right? I to I, right? That is a string of length 1, in which case if j equal to I, when does A derive length 1 string? Only if there is the rule of that form, right? And if j is greater than I do the obvious recursion. If there is a rule A, it goes to BC and an index h, such that B derives I to h and C derives h plus 1 to j. Okay? And these are sub-problems because the length of both these strings is small, smaller than the length of the original string. Okay? And that's all I want to say about this CYK algorithm, it is called. Okay? Yeah? And so let's do some basic calculation. What does it do? If the number of non-terminals in the grammar is r, right? The number of problems is what? R times n square, right? Substrings and number of non-terminals, right? So r times n square. So we need to have a table with that size. So the space will be r times n square. Now we have to say, how much time does it take for me to evaluate a problem when I have all the previous ones? You can check that it takes, if you do it naively, n times the number of rules, okay, in the grammar. So where n is the length of the string and the p is the size of the number of rules. You can be a little bit more clever. And the total runtime of this algorithm, if you do it naively, is this multiplied by that, which will get number of rules times r, the number of non-terminals, times n cubed. And this is a polynomial time algorithm because this is all polynomial in the input size, right? Because I have to write down the grammar, right? R is R and P and all of them are polynomial in the input side. Is it okay? This is a very simple high-level thing, nothing complicated here. It turns out that this is really too slow for any real practical problem, right? If you want to solve, I mean, if your compiler takes n cube time times the size of the grammar on your C program, you will not see it compile. Okay, it's too slow. So in fact, most programming languages are not actually, they are very restricted subclasses of context-free grammars. Why do they do it? So that the parsing becomes much more efficient. If you let it be a very rich context-free grammar, then you'll suffer from this n cube time. Okay, and your program can be huge, no? Your program, n, remember, n is the length of your program in characters, right? If n is like, you write a 100,000 line piece of software and it takes n cube time to compile it, you won't be happy, right? But the underlying problem in parsing is really dynamic programming. Okay. So again, from a language perspective, we see to decide whether a string belongs to a context-free grammar, we can do it in polynomial time efficiently, but the technique we need is dynamic programming. Okay? So I'm not going to go into, this is a little bit involved, I'm not going to go into details of this, but I just want you to know that DP is very important in programming language design, right? You will actually see the implementation of this algorithm, some details and all that when you do 421, if you have not already done 421. Yeah? Okay? Questions? Yeah, this is called CYK algorithm. It is named after 3 people who came up with it independently in the early days of programming language design, right? It's Falk, Younger, and Kasami. All 3 of them came up with it simultaneously, roughly. So the thing is, I kind of glossed over this because epsilon we have to skip, because in context-free, when you do Chomsky normal form, only S is allowed to derive epsilon, nobody else. No, I mean, it's a simplification so that you get rid of epsilon. Basically, you assume that epsilon is not allowed. Okay, so that's why you can do this. Okay, so yeah, it's a little bit okay. It's a technical point, yes. Otherwise, you can't do the recursion, as I said. Yeah. So no other, no non-terminal other than S is allowed to derive epsilon. So okay, all right, good catch. I wasn't sure. You want me to run an example to see how this works, or you're okay? On this grammar, do you want me to run it, or just to see what is going on, or? Yeah, okay. Okay, here is a grammar and here is a string, right? I really don't know this grammar. I just copied it from somewhere, okay? So what I'm saying is that the reason to do it is that I want to run the algorithm, not really try to understand this one grammar. You see, I want to do it mechanically, right? That's the point of the whole exercise. I don't want to know what this grammar is. Any grammar, any string, I should be able to run my algorithm, right? Okay, recursively, right? So what is it really doing, right? To know whether this string is in the language, what we do is we say, okay, 0, 0, 0, 1, 1, 1, right? Okay, if you look at it bottom up, what we need to first compute is, for every substring of length 1 and every non-terminal, first we have to decide whether that substring is derived by that non-terminal. So how many substrings of length 1 are there here? 6, right? But they're all very similar, right? So what are all the substrings of length 1? This, right? For every such substring, we have to figure out, for every non-terminal, whether that non-terminal will derive that substring. Okay, that's a lot of work, but it's polynomial amount of work. So can we, what derives 0? A derives 0, right? So basically, for all these 3 substrings, only A will derive them. Yeah? And for all these 3 substrings, only B will derive them, right? That's easy. Yeah? So we store it somewhere that, for substrings of length 1, each of the substrings A derives them. Only A and the others don't derive it, right? Okay, we kept it somewhere. Now we go to substrings of length 2. Okay. So okay, 0, 0, 0, 1, 1, 1. Now substrings of length 2 are, this, 0, 1, 1, 1, 1, 1. Okay. So the interesting things are 0, 0. In this case, 0, 1 and 1, 1, right? Those are the 3 distinct substrings, right? Who derives 0, 0? Okay. Does A derive 0, 0? How do you figure out whether A derives 0, 0? to check whether A derives 0, 0, we say, we figure out a split of 0, 0 into 2, right? Okay, there's only one split for a 0, 0, right? Non-trivial split, so 0, 0. And A should have a rule, right? Does A have a rule here? A has no such rule, right? Which A goes to BC and then each of them should derive 0 and 0. There is no such rule. So A cannot derive 0, 0, right? Okay, does B derive 0, 0? You can check that B doesn't derive 0, 0. Okay, when I say I can check, you apply the recursion. You split 0, 0 into 2 strings and then look at the rules for B and then check if they can derive the length 1 substrings, right? So, okay, who can derive 0, 0? Well, we have to check X. Can X derive 0, 0? Okay, no. Who can derive 0, 0 then? Y could derive 0, 0? No. Okay. And what happens here then? Sorry? Did I make a mistake? Nobody can derive 0, 0? Okay, nobody can derive 0, 0. Okay, all right, good. Yeah. Okay, now what about 0, 1? Who can derive 0, 1? Y can derive 0, 1, right? Why? Because Y goes to, we split 0, 1 as 0, 1, and we know already that A can derive 0 and B can derive 1 because they're length 1 substring. So we can say that this guy can be derived by Y and also somebody else. S also, right? So we know that, and nobody else, right? And 1, 1 cannot be derived by, again, by anybody, right? Okay, now we go to the substrings of length. We are done with substrings of length 2, right? Yeah? Okay, now we have to go to substrings of length 3. Okay, this one, 0, 1, 1. Okay, there are 3 substrings: 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, right? Okay, lot of work, right? That's why I say cubic time, right? Okay, how do we figure out, say, 0, 0, 0? Okay, there are essentially 3 possible splits of, 2 possible splits of this, right? 0, 0, 0 or 0, 0, 0, right? And for each of them, you have to try, right? The rules of, you fix A. You ask, does A derive 0, 0, 0? Okay, you can check, right? Is there a rule of A going to BC and a split, and you try all of that, and you don't realize A doesn't derive 0, 0, right? That's the algorithm, okay, right? Does it make sense now? Okay, you try substrings of length 3 because you already know all the answers for substrings of length 2, and you know all the rules, you can check, right? And then you go to substrings of length 4, and finally you get to the full length n, and when do you say the answer is yes? If S derives substring 1 to n, the entire length, then you say yes, otherwise no. Yeah? Okay, the output is, does S derive the entire string 1 to n? Yeah? So that's how we do it. Yeah? It is polynomial time algorithm, but it's very slow because you are doing n cube work roughly. Yeah? N cube times the number of rules times the number of non-terminal. So it's a very slow algorithm, okay? But it's still a valid algorithm, right? Valid in the sense it's a correct algorithm and it's polynomial time algorithm. And this is the only way to do parsing in your language, by the way. There is no other way, okay? The only thing you can do is you can make your grammar restricted so that you can make this algorithm fast. And that's what real programming languages do, okay? You trade off expressivity versus efficiency, and that's a classic example of DP in computer science, right? One of the most useful applications is that. Okay, so I hope you've seen enough of DP. Yeah, I hope you got the hang of it, right? It's a very powerful technique, but it's a subtle technique. There are many. It's a building block in many other algorithms. So we'll see more examples of DP in more complicated contexts. Okay, so we're not done with it. It's just one tool, right, in an arsenal. Any questions before we move to another important topic? We'll go slow because I know you're tired already. Yeah? Okay? Yes, the idea of DP is not to look bottom-up thing, because if you try to understand the bottom-up thing, you'll get confused, right? The bottom-up thing should be mechanical. The top-down should be the derivation of the correctness so that you don't think again after that, okay? Recursion allows you to clearly understand the correctness, and then the implementation should be mechanical so that you don't get confused again, yeah? Otherwise, if you are somewhere in the middle, it's not good. Okay, so next few lectures will be on graphs, okay? The graphs, many of you have seen graphs in 225, right? And some of you may think, he's wasting our time doing DFS, BFS, I know all about it, right? So I want you to be a little bit more cautious than that, okay? Mainly because even though you have seen graphs in 225 and maybe elsewhere as well, the point of thinking about them algorithmically is to get a deeper understanding of both what the algorithms are doing, right? And there are many interesting properties that are not obvious in a first understanding of the algorithm. And secondly, to also pay attention to the structure of graphs which underlie many algorithms, okay? Graph theory is, as you know, a very powerful and important topic, not only in computer science, but in mathematics and combinatorics and so on. And algorithms and structural properties of graphs go together, okay? To get better algorithms, you need to understand not just algorithms, but you also need to understand some math, right? As I said. In the context of graphs, it is knowing a little bit about graph theory. So even though you see that some of the algorithms are kind of recapping what you have seen before, we'll try to put a little bit more structural perspective on it so that you can use them effectively and use them also in reductions and so on, right? Okay, so everybody knows graphs to some extent. I assume that you realize that they're important, right? The first thing I want you to think about is undirected graphs are very different from directed graphs from a structural point of view, okay? They're not the same, okay? So we will need to work with both undirected graphs and directed graphs, right? There are a lot of differences in how we deal with them, even though some basic algorithms are essentially the same, right? They look the same, but they're doing slightly different things because the structure is different. Okay, so we'll start with undirected graphs because they are easier in some ways. So a graph is just a set of vertices, a finite set of vertices, and a finite set of edges. And in undirected graph, really there is no direction to the edge, right? And an edge is simply a pair of vertices, right? Because there's no orientation to the edge, right? So even though there is no orientation, ideally we should write an edge as just a set of two elements, right? This vertex and that vertex, okay? But somehow technically and for algorithmic purposes that is a little bit painful, so we still use the directed notation of an ordered tuple. When we write 2, 5, it's not really in an undirected graph the edge is going from 2 to 5. It's really that we are representing via 2, 5 that these two are the endpoints, right? Or 5, 2 is the same as 2, 5 in an undirected graph. There is only one object. It's a small point, but it's an important point, okay? Okay, so everybody knows what an undirected graph looks like. Why are graphs useful? So it's kind of this kind of modeling, a lot of students struggle with. So let me just do it for fun, right? So many of you have seen this problem. I remember doing it when I was a kid, right? Getting very confused, right? So Missionaries and Cannibals, right? So how many of you have seen it already? A few, okay. If you've not seen it, well, okay. Well, here is a puzzle, right? There are 3 missionaries and 3 cannibals, 1 boat, 1 river. Okay. Boat carries only 2 people at a time, right? Must have at least 1 person, otherwise the boat can't go, right, across the river. They're all sitting on one side of the river. They must all get across. Okay. At no time can the cannibals outnumber the missionaries. That means that if on the left side of the bank, on one side of the river, 2 cannibals and 1 missionary is left, not good. Okay, or either way, right? So now the puzzle is: is there a way to move all of them from the left side of the boat to the right side of the left side of the river to the right side of the one bank to the other? So on the face of it, if you look at this, there is no graphs involved in it, right? You can sit down and try all possible things, no? Yeah? You say, you know, when you're a kid, you know, when you're 10, you can give this puzzle, and then people will start like, try this, try that, try this, try that, right? Okay? But, you know, we are in computer science, so we should think a little bit more abstractly, right? How can we catch this as a graph problem? Okay? This is a technique that is very useful in many things that you'll see. Okay? So think of the state space, right? Okay? What is the state of the puzzle, or what we're trying to do, right? So you say, okay, there are some people on the left side of the river and some people on the right side of the river, right? Okay. So you represent the state as a vertex. So for every potential state, you create a vertex, right? So here is one way to do it, right? So you say, okay, what is the initial state? The initial state is all of them are on the one side of the river, right? So we're saying, you know, we're not interested in who the actual missionaries are. So there are 3 missionaries and 3 cannibals, and the boat is also on the left side. That is the initial state, right? Okay. Where do we want to go? We want to go to this state, no? Where all the missionaries and all the cannibals are on the other side of the, along with the boat. Yeah. Okay. Now the thing is, you know, what does the rules allow us to do? The rules allow us to go from one state to another state, no? Yeah? So, okay. So, from this state, the rules allow us to go to what? This state, right? Why is that? Because I can take the boat, right? And take 2 cannibals and go to the other side. That is a valid move, right? So, we represent by the move, the edges are allowing us to go from the one state to the next state, right? So, you can look at this. From here, I can go here. From here, I can go here. Right? Right? These are the only valid things that I can get to, right? Okay? So you will see that these are the only possible edges without the cannibals eating up a missionary, right? Okay? Is that okay? What we're doing? We're modeling states via vertices, right? The edges are allowing moves, valid moves. And you see that, you know, there is no way to go from there to here. Yeah, because they're in disconnected components, right? Okay, so you realize, we can't do it, right? So, okay? Yeah, because you can't go from there to here by following the rules, right? How can you go? Because there are no edges. Because we want to be here, no? This is our final goal that we want to get to, right? No, because how will you go from here to here? No, but the boat is here. Okay? Okay? The boat can't, it's not self-driving boat, not there yet, right? Yeah, 2017, I know, the puzzle has to be updated, right? Okay, but you see, it's very simple once you have the language of graphs and state spaces, okay, to solve any puzzle you want, except that the efficiency of the solution may not be great because the algorithm may create a graph whose size is exponential in the state space of the puzzle, okay? But most games, puzzles, you can easily solve using graph search, right? That's an important technique to keep in mind, that you can make any puzzle into a graph search automatically, okay? That's an important thing. Okay, notation. Edge is 2 endpoints U and V. Multigraph. What is a multigraph? It means that I allow multiple edges between the same 2 endpoints. In some applications it is necessary, but for this class, unless we explicitly say, we assume there are no multigraphs, okay? Okay? Because multigraphs are a little complicated for notation wise, so there are some applications where you need. How do you represent a graph? We all seen in 225, there are 2 ways of representing a graph typically. One is the adjacency matrix representation, the other is the adjacency list representation. Yeah? What is the adjacency matrix representation? You have a matrix which is vertex by vertex, V by V, and you put a 1 if there's an edge between U and V, 0 otherwise, right? So it's a n by n matrix, but that's very inefficient if the graph is sparse, right? It's n square space, while the graph may have only, linear number of edges, so Okay, it's not. But what is the nice thing about adjacency matrix? Whenever you want to know I and j, there you know that there is immediately you can query and get. But we will not assume this. So the adjacency list representation is, everybody knows, for every vertex you list out all the vertices that are adjacent to it. So the amount of space you take is linear in the number of edges. Okay, so that's an efficient representation, right? Okay, and you can do some tricks. Okay, but I want to be, why am I spending so much time on the obvious things? Because we'll all get confused when I discuss algorithm. So let me propose a very concrete representation to you so that we are on the same page. Because some operations can be done in constant time if you make some assumptions, whereas you don't make assumptions, right? So here is what we assume, right? It will make our algorithms a little easier to describe and make them efficient. You assume without loss of generality that the vertices are numbered 1 to n. Okay? You also assume without loss of generality that the edges are labeled 1 to m, where m is the number of edges. Okay? Arbitrarily, we don't care. Okay? Edges also have numbering. Okay? E1 to em, V1 to Vn, somehow, right? Somebody has ordered them. Okay? And you can store the edges in this single array where when you say E10, we know that it is there in 10th position. So that's very important, useful. Okay? Okay? Now we have the adjacency lists are stored, the pointers to the adjacency lists are stored in an array of size n. Okay? So this is the pointers to the adjacency list. That means that, you know, the ith vertex is, you can access the adjacency list of the ith vertex in constant time. If you tell me I can go to the adjacency list of vertex I. Okay? And then you have a list of array, right? You can assume it's an array, right? What is the size of this array? It is a degree of the vertex. Okay? And you can put here information such as the index of the edge, so that you can go back to that thing and you know what the other endpoint is if you want. Okay? So why is this important? Because once you have this indexing from 1 to n, you can do some operations in constant time which otherwise will not be obvious to you. Okay? Alright? Given any adjacency list representation, you can create this data structure in linear time, statically. Okay? Alright? We'll use this simply because it will help us save some hassle. You believe me, you will ask me questions later on that, you know, why can you do this in constant time? Okay, because, yeah. Ej means the edge j. I number the edges arbitrarily, 1 to m. I have 100 edges, they're called, this one is E1, that is E2, right? And I store them in an array. Okay, so connectivity, in an undirected graph, what is the connectivity? I is connected to j means what? This is a path from I to j, right? Yeah, so that's what connectivity means. You know what a path is, right? Yeah. A path is a sequence of vertices such that every two of them are adjacent ones are connected by an edge, right? Okay, when I say a path, it does not mean a walk, okay? A path is a simple thing, that means I can't repeat vertices, okay? Some people distinguish, this is a notational issue, it's not a big technical issue, right? There's a distinction between a path and a walk, okay? We'll come to that. Okay, path does not allow vertices to be repeated, okay? A cycle is again a closed path, right? Again, no repetition of vertices, okay? And I will use the term later on. A walk is a sequence of vertices where vertices can be repeated, right? And the same thing will say a tour is a cycle or where vertices can be repeated. If I simply say path or cycle, no vertices should be repeated on it, okay? It's again notational thing, right? Nothing complicated. Okay. And what is the connected component of U? It is the set of all vertices connected to U, right? Including U itself. Okay, so obviously from what you have seen already, when you think of an undirected graph, what comes to mind first, right? The simplest understanding of an undirected graph is what are its connected components, right? Yeah? Agreed? Alright? So you should not assume immediately when you think of a graph that is connected, right? That the simplest structural reason to pay attention to a graph is, oh, what are the connected components? Here there are only two connected components, right? It's an equivalence relation. So algorithmic problems, what is the first thing you would want to know? I give you a graph and you compute for me all the connected components, or I give you a vertex and you say, what are all the vertices that are connected to this vertex, right? Okay, these are the simple algorithmic problems, right? Okay, we know how to solve them, right? What will you use to solve them? too easy, right? Okay, you may say DFS or BFS, right? You know, you've seen this, okay? But I want us to not think about DFS or BFS because they have specific structural properties that allow us to do more than just do these simple problems, okay? We'll see that. But there is something even simpler, which is just basic exploration, okay? If I give you a graph, you don't have to think about DFS or BFS, okay? Those are concrete exploration strategies, okay? So, but I just want us to think of a simpler algorithm to search a graph, right, from a vertex U, okay? So you start a vertex U, what will you do? You want to find out all the vertices that you can reach, okay? How do we do it? Well, it's a very simple algorithm, right? You do it inductively, right? Okay, what can you reach? You can reach itself, right? And then in one step you say, what can you reach? Well, you know, you find the edges and neighbors, right? Okay. And at any point, you do, I mean, that I'm not trying to do breadth first search, right? At any point, you have a set of vertices that you have already reached. What else can the algorithm reach, right? What else can be reached? You expand that set S by saying somebody else can be reached if there is an edge from S to that vertex, right? Yeah. So you maintain a set of vertices that we have already found a certificate that we have reached that set, and you increase that set by looking at, is there any edge from this set to outside the set? If there is, I found one more guy that can be reached, and inductively you increase the size of the set. Yeah, that makes sense? Yeah. So that's a more basic strategy than saying I will do depth first search or breadth first search. I want us to keep this in mind because, you know, the more basic we have, the better we understand what is going on. It's not really about DFS or BFS, okay? All right? In fact, DFS and BFS have so that's all this algorithm is doing, right? You know, it keeps track of whether I visited a vertex and a set S, which is all the things that I've seen so far, and then it's a slightly better implementation than what I gave. It makes sure that it doesn't explore a vertex more than once, okay? All right? And I mean, this is not hard, you know. You know, I'm just giving this as I call this a simple algorithm basic graph search. See, whenever you want to use a graph search, don't say DFS or BFS if you don't really are not using the properties of DFS or BFS. Okay? This is not that you shouldn't say it. All I'm trying to say is that in your mind, you should say, all I want is really, given a vertex, what are all the vertices that you can reach? That is the black box you should think about. Okay? Not whether I use DFS or whether I use BFS. Okay? I know that given a graph and a vertex U, I can find the connected component of U efficiently. How? Using a simple search algorithm. Okay? The properties of that search algorithm you should not exploit unless you need to. Okay? If you're using DFS, okay, why are you using DFS? Well, okay, it's just an example of a simple search algorithm. Okay? But there will be examples where DFS is very important because DFS has some very important properties in the way it explores a graph, which can be exploited to get something better than what if you just did basic search. But then we say, aha, that's why DFS is important. Okay? Same thing with BFS. BFS does it in a certain way, which gives us extra information. If you don't need the extra information, don't use it because then you're thinking cleanly, right? All I need to know is, do I need to find the thing, right? Okay, do I want to run an algorithm to do the search? Yeah? Yeah, how does the algorithm work for search? Yeah? No? Yes, no? Everybody knows this? Or should I do it? Don't be shy.
Yeah, do it.
Do it, okay. He's the man, okay. Okay, we start, suppose, I mean, the exploration has to start from some given vertex, right? That's the input to the exploration. If I start at 1, what should I do? 1 is in my set, I take out 1, I look at my neighbors, I find 2 and 3 because they are not already visited, because they are not, initially I mark everything as not visited, and I look at, I explore 1, I get 2, I add an edge, this is going to create a tree, but I add to my set 2 and 3 because I have to explore them, right? When I first find a new vertex, I had to put it in a list to explore further because I need to explore its edges, right? Okay, I'm done with 1. I start with S equal to 1. I took it out. I explored 1. I found 2 new vertices, 2 and 3. I put them in the list. Now I have to take 1 more vertex out of the list arbitrarily. I can take 2 or I can take 3. That's why I'm writing it as a set. I take out 2. What do? I explore all the edges out of 2. What are all the edges out of 2? I have an edge to 1, 4, and 5, right? Yeah? 1 is already visited, so I don't do anything, right? But I find 2 new vertices, and so I took out 2, so now S becomes 3, 4, 5, right? Yeah? And I can pick any vertex from S again. In this basic search, I don't care, right? What do you want to pick? Anything you want, right? Should I pick 4? Let's pick 4, right? I mean, I'm doing it arbitrarily. If I pick 4, what do I get? I explore 4, what do I get? Do I get anything new? I find that 2, all the edges around 4 are 2 and 5, and I say I already found 2 and 5. I don't need to do anything. So S becomes 3, 5, right? Yeah? Okay, simple algorithm, right? And I'm just maintaining the set of nodes that I found that I have not explored yet. And each time I take out a vertex, explore it. If I find new vertices, I add it to the list and throw it out. Yeah? Okay? So I take 3 out maybe, and I say, okay, I found 1 edge to 5. 5 is already explored. 7 and 8. So I can create 7 and 8. And now S becomes 5, 7, and 8. And I take out 5. I find 6. So S becomes 6, 7, 8. And then I take out 6. And from here, I don't find anything else, right? So I get 7, 8, 8, and then S becomes empty, and I'm done, right? Yeah? So what is the running time of this algorithm if I implement it this way? N plus M, right? I'm touching each edge how many times? Twice, right? From both endpoints, I'll touch that edge, yeah? And each vertex I only touch once, yeah? Okay? So it's N plus M, right? It is not using any data structures, no? It is only using S as a list. I don't care how a list is organized or anything, right? I just pull out something from the list, okay? Simple algorithm, N plus M, okay? Okay, it obviously creates a search tree, right? And to find all the connected components, what would you do? So this is basic search. I'm not using any data structure other than a list. I'm maintaining S in a simple list. I don't, okay? This is basic search, okay? And you can easily show that, when you finish this algorithm, you get the connected component of U, right? Connected component of U is a set of all, right? Okay? Okay, it takes M plus N time, blah, blah, right? And what are BFS and DFS? They're special cases of this search, right? What is the only difference? What happens, how do we get DFS as a special case of this? What data structure will give you DFS? Yeah, right, a stack and, okay, but I don't want you to think like that, okay? It's true that DFS and BFS are special cases of this search, but they're interesting not because they use some stack and queue, right? What does using a stack do in terms of the properties that DFS has? What does a queue do to the properties of BFS has? Okay, and we'll see that we should think about it. Search tree is what we already did, right? Okay, that is undirected graphs. Directed graphs are different beasts. Okay, you should not confuse directed graphs and undirected graphs. You should know when you're working with a graph whether it's directed or undirected. Why are directed graphs different? Okay, because, well, they are directed, right? Well, that means that every edge has an orientation, right? Okay, so you have a graph, vertices, and the edge has an orientation, which means that the pair is now ordered, right? U to V doesn't mean there is an edge from V to U. So how many edges are possible in a directed graph? If there are n vertices, what is the maximum number of edges in a directed graph? Sorry? How many edges are possible in a directed graph? N square, right? Because every pair is possible, but in an undirected graph, how many edges are possible? Yeah, maximum number of edges possible. Only half of that, right? Or less than half of that. N choose 2 is the only number of, right? Because you can't have, the edge is one direction, right? And there is no direction to it, it's just an edge, right? That's the difference, right? Okay, so don't assume that U to V means that V to U is there, or that both can't be there. Both can be there, right? U to V and V to U are separate edges in a directed graph. Okay, okay. Obviously you can. So again, Now here is an interesting question. Directed graph representation, we have to think now. What should we store for a vertex? What edges should we store for a vertex? Outgoing edges, incoming edges, what should we store? Why? Yeah? Yeah, so there is no, there is no good reason, right? Actually, it's just sort of like the convention is that we store the outgoing edges, okay? But there are algorithms where you need the incoming edges too, okay? So why do we not store the incoming edges? You can, it's up to you, right? So the reason we don't store it is just that extra space it creates, right? But it's only doubling the space, right? So that's maybe important in a big graphs, right? So we will assume for simplicity only, this is not because it's convention, that we are only going to store the outgoing edges, okay? That's just a convention, right? If you want the incoming edges, you can scan the graph and create all the incoming edges in linear time, right? Okay. Okay. So when you're thinking about an adjacency list of a graph, we have to distinguish out and in. Okay. So when we'll assume, we'll use the terminology out and in to make sure that we are not getting confused. Okay. And when we say adjacency of U, we are only going to assume it is out, simply again by convention, not because it is actually technically meaningful. All right. Okay. Okay. So again, path in a directed graph is a directed path. When we say a path, the edges have to be oriented in the right way, right? And same with cycle. And again, we'll think about a walk. And now there is a little bit of a technicality that you may be able to reach V if there's a path from U to V, right? That doesn't mean V can reach U, right? Yeah. Okay. So that is asymmetric. So we'll use reach U to be the set of all vertices reachable from U. Okay. That is just a notation. And as we know, in directed graphs, the reachability relationship is not symmetric, no? You may be able to reach V, but V may not be able to reach U. So how should we think about a directed graph? I give you a directed graph like this. What does it, what image does it generate in your head? Right? It just looks like a graph, no? But when you see a connected components of a graph, we immediately say, these are connected components, right? But when you look at a directed graph, it looks like it is connected, no? Does it, right? Okay, so it is more subtle, right? See, you can't immediately tell what's going on with a directed graph. Yeah? Yeah? So sort of looks like a bit more complicated because the reachability relationship is asymmetric, right? So, okay. So there is a way to think about directed graphs and which is nicer. Is there a notion of connected components, or how should we think about a directed graph connectivity? And the right notion is the notion of strongly connected components. Okay. Okay. What is so we define something called U is strongly connected to V means what? U can reach V and V can reach U. Okay. So if that happens, we say U is strongly connected to V. Now, sorry? No, a path from U to V and a path from V to U, not a single edge. Okay? Okay. So this relationship is a symmetric relationship, right? Obviously, if U is strongly connected to V, V is strongly connected to U. Yeah? But it's also transitive. That means U is strongly connected to V and V is strongly connected to W, means U is strongly connected to W. Okay? So this is an equivalence relationship, and it partitions the graph into strongly connected components. Okay, that's the right way to think about a directed graph. If you want to think about connectivity, what are the strongly connected components in this directed graph? We'll come back to this, but I just want to give you a preview, right? Okay, the strongly connected components of this directed graph are this one. No, sorry, I made a mistake here. Somebody noticed that? Okay, okay. Okay, so this is wrong. Okay, this one, and this two. Okay, we'll see it again. Okay, that's we will. Let's not worry about it. It's a little late, but that is how you think about directed graph connectivity. It's important to distinguish them.